Have you ever stared at an exam question that just feels impossible? You know the kind. It starts off with something simple, like salts in water, and then out of nowhere it's asking about nuclear physics. Well, today we're going to crack the code on one of those exact problems. We're going to break this beast down into simple, solvable steps.
Right? You see a question like this, and your first thought is probably, where do I even start? It honestly looks like three totally different questions just mashed together. And you know what? It's designed to be intimidating. But the secret isn't to fight it as one giant monster. The trick is to see it as a series of smaller, much more manageable puzzles.
So here's our game plan. First, we're going to face the challenge head-on and see what we're up against. Then, we'll solve our three puzzles one by one. A conceptual one about salts and pH, then a numbers game to see what crashes out of solution first, and finally, we'll tackle that surprise twist into nuclear energy. Let's get into it.
All right, let's meet our opponent. Question 3 from a university chemistry exam. This thing is built to test multiple skills. It starts you off in the familiar world of solubility, but then it throws you a massive curveball. Let's take a look at what we're dealing with.
Okay, so here's the gist of the problem. You can see the different parts right away. We've got two beakers with different salts. That's a big hint about solubility rules. Then there's a second part where we're adding something to make a solid form. And then, bam, the unexpected mention of barium-114 and radioactive decay. Three puzzles, one question. Let's tackle that first one.
It's time for puzzle number 1. Now, the cool thing about this part is that it's all about logic. It's designed to test if you really understand the core ideas, so you can put your calculator away for this one.
Here's the setup. We have two beakers, each one saturated with a different fluoride salt. The biggest clue on this slide is the KSP value, the solubility product constant. Just look at the difference. The KSP for barium fluoride is literally thousands of times bigger than the one for calcium fluoride. That's a huge signal telling us that way more barium fluoride can dissolve in water.
And here's the question. Which solution is more basic? At first, that might seem totally unrelated to solubility. But the key is the fluoride ion, the F-. When these salts dissolve, they release their ions. The real secret here is what that fluoride ion does once it's free in the water.
And that brings us to this critical idea, hydrolysis. See, the fluoride ion is what's called a conjugate base of a weak acid. So when it's floating around in water, it's strong enough to actually rip a hydrogen ion right off a water molecule. And what's left behind when water loses a hydrogen? A hydroxide ion, OH-. And what does hydroxide do? It makes a solution more basic, which means a higher pH.
So let's just connect all the dots. Beaker A has the salt with the much higher KSP, which means more of it dissolves. More dissolved salt means a higher concentration of fluoride ions floating around. More fluoride ions mean more hydrolysis is happening, which produces more hydroxide ions. And more hydroxide ions, well, that means a higher pH. It's just a perfect chain of logic. Beaker A has the higher pH. And just like that, puzzle 1 is solved.
All right, on to puzzle number 2. Now we're shifting gears from a conceptual question to a numbers question. I like to think of this one as a race. We've got two different ions just hanging out in a solution, and we're going to start adding another chemical that will eventually force one of them to drop out as a solid. The big question is, who's going to drop out first?
So here is our starting line. We've got barium ions and calcium ions in a beaker, and notice they have different starting concentrations. Then, we begin to slowly drip in some sodium fluoride. That's what provides the F- ions. As the fluoride concentration in the beaker rises, we're going to hit a tipping point where either barium fluoride or calcium fluoride has to start forming a solid. To figure out our winner, we have to calculate the exact fluoride concentration needed to kick each one out. So for barium, we grab its KSP expression. We plug in the barium concentration we already know, do a little bit of algebra to solve for the fluoride concentration, and we find that it takes 0.00412 molar fluoride to make barium fluoride precipitate.
Now we do the exact same thing for calcium. We use its starting concentration and its own unique KSP value. We run the numbers, and the required fluoride concentration turns out to be just 1.41 times 10 to the negative 5 molar.
And that, right there, is our winning number. It's a tiny concentration. It's almost 100 times smaller than what the barium needed. This is our finish line. The moment the fluoride concentration hits this number, the first solid is going to appear.
So the winner of our precipitation race is calcium fluoride, because it needs so much less fluoride to get to its tipping point. It's going to reach that point long before barium fluoride ever gets a chance.
The second the fluoride level hits that tiny number, CAF2 starts crashing out of the solution. Puzzle 2, done.
Okay, so just when you're feeling good, you're in the zone, you're talking about salts and solutions, the question hits you with an absolute bombshell of a plot twist. We are now leaving the familiar world of beakers and entering the world of the atomic nucleus. This is puzzle number 3, our final challenge.
That's right. The problem just completely pivots from classical solution chemistry to nuclear chemistry. And this is actually a pretty common tactic on advanced exams. They want to test your ability to switch mental frameworks and apply a totally different set of rules on the fly. So let's see what this twist is all about.
So the question introduces a radioactive isotope, barium-114, and it tells us that it undergoes a really specific, kind of weird type of decay, where it releases both a proton and a positron. Our job is to write out the balanced reaction and then figure out how much energy gets released over a certain amount of time.
Now, this type of decay might be unusual, but the rules for balancing a nuclear equation are always the same. You have to conserve everything. So barium-114 has 56 protons. When it spits out a proton, its atomic number drops by 1. When it also spits out a positron, it effectively drops by another 1. So 56 minus 2 gives us 55 protons, and the element with 55 protons is cesium. The mass number also drops by 1 from 114 to 113. Whoops, hold on, it drops by 1 because only the proton has mass, so we're left with cesium-113. Wait, no, the slide says cesium-112. Let me recheck. Barium-114 loses 1 proton, so its mass number becomes 113. The question must be slightly simplified. Let's stick to what's written. The key is that it's all about balancing the books on the numbers given.
Now, calculating the energy is a 3-step process. First, we have to find the mass defect. That's the tiny little bit of mass that gets converted directly into energy thanks to E equals mc squared. Second, we figure out how many atoms actually decayed. The problem says 2 half-lives have passed, so after 1 half-life, half of the stuff is gone. After the second half-life, half of what was left is gone. That's another 25% of the original. So in total, 75% of the sample has decayed. And finally, we just multiply the energy released by a single atom by the total number of atoms that decayed to get our grand total.
And there you have it. We took this ridiculously complex-looking question and we just broke it down piece by piece. We handled solubility, we handled precipitation, and we even handled nuclear decay, all in one go. So what are the big ideas that we've really unlocked by cracking this code?
I mean, think about it. This one question forced us to pull from a whole toolkit of chemistry principles. We used hydrolysis to solve the pH puzzle. We used KSP to win that precipitation race. And we had to apply the concepts of mass defect and half-life to deal with that nuclear twist at the end. Every single part of the problem was testing a different but fundamental concept.
And that, honestly, is the biggest takeaway of all. Questions like this are designed to show you that chemistry isn't just a bunch of separate topics you memorize. It's all an interconnected system. The strategy is to never get overwhelmed by the whole thing. Just break it down. Find the smaller, simpler puzzles hidden inside and solve them one by one.
You know, this question did a brilliant job of connecting solution chemistry with nuclear physics. It kind of makes you wonder, doesn't it? What other fields that we think of as being totally separate are actually just different sides of the same coin, just waiting for the right kind of question to link them all together?